Hello students, welcome to the lab video. As you'll recognize from having read the lab manual, this is the tensile tester. On the bottom we have the bottom plate, the springs, and the dial. And then moving up we have the bottom chuck and the top chuck. So this is where the tensile tester specimens will be loaded. Then the top chuck connects to this threaded rod. And it's this threaded rod through which force is transmitted to the test specimen from the load nut up on the top. So this is the load nut. Turning it clockwise draws the threaded rod upward. Around the base of the load nut there are lines marked in. So one complete rotation of the load nut is 1 millimeter of displacement of the threaded rod, and there are 10 graduations there, so each one of those graduations is 1/10 of a millimeter. So the load nut pulls up on the threaded rod pulls the top chuck, which pulls the test specimen, which pulls the bottom chuck, which then pulls the bottom plate up and compresses the springs, which is what we read on the dial. So we have 3 test specimens. We have steel, aluminum, and PVC. And these are what we're going to load into the tensile tester. So here's an up close of the steel piece. It has kind of a rough surface. It's dark gray. Aluminum is lighter, smoother surface. And the PVC obviously is a dark plastic. So now we're going to put the aluminum specimen into the tensile tester. So the first thing to do is remove the safety cover. And then we have a couple of machine screws to take out. So the screws come out of the chucks. And there's the aluminum specimen. So it doesn't quite fit, so by adjusting the top nut, we can get that. We can adjust the top chuck and get the aluminum so it just fits in there, and so all the holes line up. Then the screws go back in. That was the bottom screw. Here's the top screw. And so tighten those down finger tight. And then the Allen key here, snug them down a little bit further so there can be no slippage. And we put the safety cover back on because safety is very important. Now the gauge may not be exactly zeroed, and what we want is for the gauge to read 0 just as the test specimen starts to demonstrate tension, starts to pull the bottom plate up. So we wiggle the load nut or move the load nut a little bit until we just see movement, and then adjust the outer bezel on the dial to 0 it. So now it's ready for testing. So the aluminum specimen is loaded, and over on the right hand side of the screen you'll see the load nut. And for the first few measurements you should see approximately linear behavior. And so I say approximately, it's quite challenging to move the load nut exactly the same amount each time. And so that's potentially a source of error for the first few readings, is that small errors in the position of the load nut lead to large errors in the strain. So I've sped the video up quite a bit, as you'll notice, and we move through yielding. Note there it just broke. And so we've removed the aluminum piece, and now you can see, compared to its original dimensions, it has slightly elongated. So now I've loaded the steel specimen, and the behavior is very similar to aluminum, except that for steel there's a higher yield point and a higher tensile strength, so it takes many more turns of the load nut before we finally reach the breaking point. And now the video is sped up quite a bit. As I say, it takes many, many turns to reach the breaking point of the steel specimen. Now we're close to the breaking point. You'll see that the steel is stretching in order to decrease the stress. And compared to the aluminum, the steel has a much louder pop because it was storing much greater energy. Again, you can see a little bit of extension on the steel piece due to plastic deformation. So now the PVC test sample is loaded, and as a polymer and a very non-crystalline polymer, the PVC material behavior is very different than the two metals. So it has a much lower yield point. So it starts to yield after only a few turns of the load nut. So I'm actually making smaller turns of the load nut for each reading. But you'll see that when it gets up to about 0.1 millimeters of displacement, so that's 10 on the dial gauge, that we really can't push it past there because it just starts stretching past the yield point, and everything past here is plastic deformation. Now, because it has such a large ductile region, at this point, instead of making small turns, I've gone up to making 10 turns at a time, so that's a full centimeter between readings. But you see, even turning very quickly, that the needle is falling back in between half twists. All right, now so you're at the very end. There it's broken, but you could see it at the very end that we were finally starting to get a little bit more tension in the specimen, and it was pulling up the bottom plate and creating greater displacement. So now that we've gathered some data, the next thing we have to do is analyze the data. So you've actually been supplied all of your data already as an Excel spreadsheet. And if you've never used Excel before or you're a little rusty, I'm going to show you how to do the data analysis. So again, if you haven't used this before, it's an incredibly useful program. So everything is built around cells, and then the cells exist in rows and columns. So the first thing we'll calculate is the force. So I click a cell where I want a formula, and then up here I can enter the formula. So we know the force is related to the dial indicator reading, and that's multiplied by the spring constant. For our springs, the spring constant is 100 newtons per millimeter. And the amazing thing here is down in the lower right hand corner there's this kind of dark green little square, and if we put the mouse over that square we can pull the box down, and now it fills in the formula through every cell we pull the box through. And so we were referencing a cell in row B, and it pulled that reference cell down to match the boxes as we were pulling the cell in column C down. So that's very useful. Extension we know is the load nut reading minus the dial indicator reading. Again, just pull it down. Stress is force over area. We've calculated the force already. For the area, I'm going to take the width times the depth, so that's the cross-sectional area. Now, if I pull this down, we run into problems because it's also pulling down the two cells that were the width and the depth. So we don't want that. So when we write this formula in the first cell, I can highlight the cell or put my cursor near the cell for the depth. And now on the keyboard, if I press F4, you'll see it's put little dollar signs in front of the column and the row, and the dollar signs mean that that value is locked into place. And if we press F4 again, we can lock just the row or just the column, or unlock both, or lock both. We'll do that again, F4. Those cells are now locked in the formula, and now when we pull this down, they haven't moved. Strain is change in length over original length. The extension is the change in length. Here's the original length. And again, we want F4. Pull that down. So we've done the numerical analysis on the data. I'm pretty happy with how this looks. In Excel, there's not an easy way to handle significant figures. If you wanted, however, to change how many decimal points are displayed, it is easy to do that. So maybe we want to put one decimal place. Instead of having 0, 0, 0.00, 0.0, 0.000, we can make those all the same. So up here where it says number, you can either use these buttons here to increase or decrease the decimal point, or you can say this is a number, or some other format, scientific if you want, number, increase, decrease, like that. Of course, maybe it makes sense to have this one with multiple decimal places, since all of the ones below it do. Now we want to add a plot, a graph, And the type of graph we want is called a scatter plot. So a scatter plot is often the right type of plot to use for data because data represents discrete points of information, and so we want discrete markers on our plot. So if we right-click on the plot area, we can go to Select Data, and now we're going to add some data. If you want, you can give the data series a name. So this is data for acrylic, so PMMA, stress, strain, data. The X values are the strain, and the Y values are the stress. Often in academic papers, graphs have the grid lines removed. It's really a matter of personal taste, but I think we'll remove these lines. So no line for the vertical, no line for the horizontal. Now if I click the numbers at the bottom, and here we have axis options, and so instead of grid lines, we will have tick marks. I like tick marks that cross the axis, but you can have tick marks that go on either side of the axis. I don't think it tells us anything useful to have a decimal point here on the graph. So under numbers, we'll have no decimal places there, and so we should just get whole numbers. Similarly down here, I think we can go with just 2 decimal places. That looks cleaner to me. We should give our axes titles. So under Design, up at the top, add a chart element. The horizontal axis, this is the strain, which is unitless. And now the vertical axis, this is the stress, and that has units of MPa. So this looks pretty good. I'd be satisfied putting this into a report. On the other hand, there is a little bit more analysis we could do. So part of this clearly looks linear. We have a little bit of a discontinuity here, but that shouldn't worry us too much, particularly at very low readings here. It can be very difficult in moving the load nut to be precise about 0.2 millimeters, and so even small errors in that 0.2 millimeters as a percentage error can be quite large, and so you may have quite a bit of scatter through the first 4 or 5 data points. Don't worry about it, but overall it looks like up until about here things are linear. So let's add another data series. For the linear region. That was wrong. The strain is the x-axis. Stress is on the y-axis. So we've got a a new data series that's just in the linear region. And now if we want to find out the slope, one way to do that is by adding a trend line. By default, that's a linear trend line, which is good. We can force it to go through 0. And so, although some of the early data seems not quite to line up with it, again, that shouldn't bother us because we expect more scatter there, but that's a pretty strong linear trend. And now if we put the equation out there, since this is in slope-intercept format, and we set the intercept to 0, this slope is the elastic modulus. Now, when you present this in your report, you probably shouldn't have this equation or this trend line on here. It's just useful for analysis. Alright, so hopefully that gives you some information about how to analyze your data and how to use Excel. Thank you very much.